Good morning, ma'am. My name is Shiva. I am from CSCF section in SRIT College. My topic name is about intrinsic semiconductors. Introduction to intrinsic semiconductors. Intrinsic semiconductors are pure materials that have no significant dopant atoms present. They exhibit electrical conductivity that is intermediate between conductors and insulators. Silicon and germanium are the most commonly used intrinsic semiconductors in electronic devices. Structure for intrinsic semiconductors. Intrinsic semiconductors are typically crystalline solids with a well defined lattice structure. Each atom in a lattice contributes 4 valence electrons, forming covalent bonds with neighboring atoms. The crystal structure can significantly influence the electrons' properties of the semiconductors. Energy band structure. The energy band diagram of intrinsic semiconductors consists of a valency band and conduction band. The energy gap or band gap between these bonds determines the semiconductor properties. At absolute zero, electrons occupy the valency band and the conduction band is empty. Charge carriers in intrinsic semiconductors. Charge carriers in intrinsic semiconductors include electrons and holes which are created when electrons gain energy. Electrons can thermal excited from the valency band to conduction band, leaving behind holes. The number of charge carriers increases with temperature, enhancing conductivity. Temperature dependence. The conductivity of intrinsic semiconductors increases with temperature due to the thermal excitation of electrons. At higher temperatures, more electrons can jump into the conduction band, allowing the greater current flow. This temperature dependence is crucial for the operation of many semiconductor devices. Comparison with extrinsic semiconductor. Unlike intrinsic semiconductor, extrinsic semiconductors have controlled levels of dopants added to modify their properties. Extrinsic semiconductors can be N-type or P-type depending on whether the dopants provide extra electrons or create holes. Intrinsic semiconductors serve as the baseline for understanding the behavior of dopant materials. Applications of intrinsic semiconductor. Intrinsic semiconductors are fundamental in the manufacturing of diodes, transistors, and integrated circuits. They are used in solar cells to convert sunlight into electricity due to their efficient charge carrier generation. Research in intrinsic semiconductor continues to explore new materials and applications in electronics and photonics. Advantages of intrinsic semiconductor. Intrinsic semiconductor offer purity leading to predictable and stable electrical behavior. Their intrinsic semiconductor allow for the development of devices with minimal noise and high efficiency. These are essential for creating high performance electronic components in modern technology. Challenges in using intrinsic semiconductor. The relatively high conductivity of intrinsic semiconductors at room temperature limits their use in some applications. Achieving the desired electrical properties often requires precise control over temperature and material quality. Understanding the limitations of intrinsic semiconductors is a critical for advancing semiconductor technology. Future directions in semiconductor research. Ongoing research aims to develop new intrinsic semiconductor materials with providing properties and performance. The exploration of two-dimensional materials such as graphene is opening a new venues of semiconductor application. Future advancements may lead to more efficient devices with lower energy consumption and in exchange functionalities. Thank you.